Hello, welcome you all. In this session, we will see the derivation of the shape functions for the 1D element for the conduction problem, and also we will derive the stiffness matrix for the element. As it is not possible in one video, we will extend it to part 2 and part 3. Okay. In this video session, we will see what is the shape functions for the 1D element for the conduction problem. Welcome back. Let us start the derivation of the shape functions for the 1D element. Conduction, it is a mode of heat transfer where the heat transfer from the higher temperature to the lower temperature. Let us consider a element. It has two nodes, node 1 and node 2. Let us derive this shape functions in terms of global or Cartesian coordinate systems. So at the node 1, it is at a distance x1 from the axis, and node 2 it is at a distance x2 from the axis. So the boundary condition of this element is at node x is equal to x1, t is t1, at x is equal to x2, that is the position of the node 2, T is temperature is T2. The field variable for the heat transfer, it is temperature. So as we have two boundary condition for this finite element, let us consider a linear element which has two constants. Okay, the field variable is temperature. To find this temperature, we are consider the linear element displacement functions. T is equal to a0 plus a1x. Okay, applying the first boundary condition, that is the field variable at node 1 is t1, t is equal to t1 at x is equal to x1. So we have this expression, t1 is equal to a0 plus a1x1. Okay, applying the second boundary condition, that is at x is equal to x2, we have field variable t equal to t2, t2 is equal to a0 plus a1. Instead of x, we write x2. Okay, let us bringing these two equations in the form of matrix, where the nodal temperatures are T1 and T2 written here. These are the nodal temperatures, and it is expressed in terms of constants. Constants are a0 and a1, So in the first equation, the coefficients of the a0 and a1 are 1 and x1. Okay, similarly the coefficients of constants, that is a0 and a1, are 1 and x2. Okay, the nodal temperatures vector, that is equal to coefficient matrix, that is equal to constant matrix or constant vector. Okay, so to find the constants a0 a1, we can write in this fashion. If this matrix come this side, it is the inverse of the matrix, 1 x1 1 x2. So let us find what is a0 a1 vector. Okay, you bring this matrix left side. So it is 1 x1 1 x2, inverse of the matrix t1 t2. We already know how to find the inverse of the matrix. To find the inverse of the matrix, first we need to find the cofactors and apply the minors of the matrix. Okay, what is the cofactor of this one? It is the opposite diagonal term, that is x2. Okay, cofactor of this x1, it is the opposite diagonal term, that is 1, and cofactor of this one, it is x1 diagonal term, and cofactor of this x2, it is diagonal term 1. Okay, so the cofactor matrix, it is x2 1 x1 1. Okay, cofactor of this one, it is x2, cofactor of this x1, it is 1, cofactor of this one, it is diagonal term x1, cofactor of this x2, it is the diagonal term 1. This is the cofactors. What is the minus of the matrix? Minus, it is plus minus minus plus, plus minus minus plus. So to find the inverse of the matrix, 1 by determinant and the adjoint of the matrix, that is you have to transpose this matrix, so rows into columns, columns into rows. So it is written x2 minus x1, and this column has the row minus 1 1. What is the determinant of the matrix? X2 into 1, that is x2, minus x1 into 1, that is x1, x2 minus x1. So determinant is x2 minus x1, 1 by x2 minus x1, and this adjoint of the matrix, that is the transpose of the matrix, rows into columns, columns into rows. So x2 minus x1 minus 1 1. So this is the inverse of the matrix, substituting this inverse of the matrix value. So a0 a1, that is equal to, this is the inverse of the matrix, 1 by x2 minus x1, x2 minus x1 minus 1 1, and t1 t2. So these are the constants. Okay, now constant vector, it is determined. Now applying the, okay, the displacement function or the interpolation functions, what we have taken to derive the shape function is t equal to a0 plus a1x. What is t here? T is equal to, it is again written in the matrix form. As we know the constants vector, we have taken in this fashion. Okay, what is the quotient of a0? It is 1. Quotient of a1, it is x. Okay, now you substitute the value of a0 and a1, that is constant vector. This is the constant vector equation, 1 by x2 minus x1, x2 minus x1 1 minus 1 1, t1 and t2. Okay, substituting a0 and a1 vector, it is written here. So 1 by x2 minus x1, it is taken outside. Multiplication of these two matrices, 1 into x2, x into minus 1, it is minus x. Okay, similarly 1 into minus x1, x into 1, it is plus x. Okay, t1 t2 as it is written here. So x2 minus x1, it is nothing but the length of the element, 1 by LE. x2 minus x1, it is the length of the element. So what is the product of these two matrices? x2 minus x1 into t1 minus of x1 plus x into t2. Okay, now the quotient of t1, it is nothing but the shape function 1. The quotient of t2, it is nothing but quotient of, that is n2. Okay, so the nodal temperature, it is expressed as the shape functions and the nodal temperature. The concept of shape function is to find the nodal temperature at any point with the help of shape functions and the nodal temperature. If you know the shape functions and the nodal temperatures, then nodal temperature at any point within the element can be calculated. Okay, this is the concept of the shape function. So by this the nodal temperature at any point, it is expressed as the shape functions and the nodal temperature. Okay, so what is n1 here? The coefficient of t1. The coefficient of t1, it is 1 by LE, x2 minus x. Similarly n2 is equal to x minus x1 by LE. Okay, we have got these same shape functions for bars as well as shaft problems. Okay, next we'll derive the strain and stiffness matrix of the 1D element. We know that to derive the stiffness matrix, we are using this strain energy. Okay, in this strain energy, if the nodal displacements and if the nodal displacement for the heat transfer problem, it is not the nodal displacement, it is nodal temperatures, where Q, T and Q are the nodal temperatures. If this nodal values, nodal temperatures are removed, then what you will get at, that is the stiffness matrix of the 1D bar element for the conduction problem. Okay, we will see in the next video session. Thank you.